With this lesson, we are going to begin a new topic, which is all to do with security. And the first area we're going to be looking at is encryption. So by the end of this particular session, you should have a deeper understanding of how encryption actually works. If you studied IGCSE in the past, you would have encountered symmetrical and asymmetrical encryption. We're just going to have a recap of that before we move a bit more deeper into quantum cryptography, which is quite exciting, really. So as usual, let's begin by looking at some key terms. Do pause the video and jot these down. There are going to be two sections of key terms, so make sure that you understand what these mean, and we'll be referring to these throughout the lesson. So let's start with the first term, eavesdropper. An eavesdropper is a person who intercepts data being transmitted. Normally you will have data which is in plain text, which means that the original text or the original document or the message before it is put through an encryption algorithm. Now, if you send data using plain text and the eavesdropper intercepts it, you can easily decipher it because it hasn't been changed. It's exactly the same as the original. So using encryption, we can turn it into ciphertext. The plain text is put through an encryption algorithm and the result is sent, and that result is called the ciphertext. Now you can create these ciphers using the block cipher, which is encrypting a number of contiguous bits in one go rather than one bit at a time. So kind of like a batch processing system. And the next one is the stream cipher, where the encryption of bits in a sequence as they arrive at the encryption algorithm is utilized. So here we don't do everything all together. So as the bits arrive, they're encrypted. Now blockchaining is a form of encryption in which the previous block of ciphertext is XORed with the block of plain text and then encrypted. And this prevents identical plain text blocks producing identical ciphertext. So you end up having perhaps the same paragraphs producing different ciphertext because you use the first paragraph, which might be the same as the second paragraph, word for word, for example. And when you pass that to an encryption algorithm, it gives you maybe a number. And then when you pass the second paragraph independently through the same algorithm, you might end up with the same number. But if we XOR the results with the plain text before you pass it through the algorithm, then that allows you to generate a different number. Symmetrical encryption or symmetric encryption is one in which the same key is used for both encryption and decryption. Now this leads to the key distribution problem, which is a security issue where somebody intercepts this secret key, they can decrypt all your messages. To avoid that, we use asymmetrical encryption, where the encryption is done using public keys, which can only be deciphered or decrypted using private keys. Public key is a key known to all users in asymmetric encryption, and private key is a decryption key which is only known to the single user. For example, in this case, it could be a bank. Quantum cryptography is cryptography based on the laws of quantum mechanics, the properties of photons. Quantum key distribution is a protocol which uses quantum mechanics to securely send encryption keys over fiber optic networks. And qubit is the basic unit of a quantum of information, also known as a quantum bit. Now let's start with the need for encryption. Why do we need it? Whenever you transmit data over any public network, be it wired or wireless, there is an inherent risk of it being intercepted by a hacker, also referred to as an eavesdropper. Using encryption helps to minimize this particular risk because encryption alters data into a form that is unreadable by anyone else. We do that through the use of encryption keys. Encryption cannot prevent the data being intercepted because you can still intercept the encrypted data, but it stops it from making any type of sense to the eavesdropper. And this is particularly important if the data is sensitive, for example, medical or legal documents, or confidential in the case of credit card or bank details. There are four main security concerns when data is being transmitted: confidentiality, authenticity, integrity, and non-repudiation. Now, confidentiality is where only the intended recipient should be able to read or decipher the data. Authenticity involves the need to identify who sent the data and verify the source is actually who they say they are. Integrity is the data should reach its destination without any changes along the way. So you don't want somebody accidentally or deliberately changing the data. And non-repudiation is that neither the sender nor the recipient should be able to deny that they were part of the data transmission which just took place. Because think about this, in the case of a bank or a banking transaction, if a customer does a transaction and later denies that transaction, the bank might have already paid the money out of their account and the bank then has a loss. So non-repudiation is basically proof that the transaction did occur or the transmission did occur. So all four are essential. And if you compromise on any one of these, that means that there will be security issues, which can lead to financial and perhaps personal loss. So in an exam, make sure you do talk about these four factors if you need to justify the need for encryption. Now let's look at plain text and ciphertext. This should be pretty straightforward. The unencrypted text, the original data being sent, is called plain text. And once we pass the plain text through an encryption algorithm, it becomes ciphertext. So the diagram on the bottom of the screen probably is a better way to illustrate what we're talking about. You take a bit of plain text, you use an encryption key, and then using that, you use that encryption algorithm to convert it to ciphertext, which is sent over the internet. The ciphertext is then passed through a decryption algorithm, which uses a decryption key to unlock it back into plain text. So when we're encrypting a text, a block cipher is normally used, and here the encryption algorithm is applied to a group of contiguous bits. For example, you might choose 128 bits, 256 bits, and so on. We don't use one bit at a time, which is known as the stream cipher. And with a block cipher, each plain text block is XORed with the previous ciphertext block and then encrypted. And this is known as block chaining. And this prevents identical blocks of plain text producing the same ciphertext each time that they are encrypted. So make sure that when you're talking about plain text and ciphertext and how the encryption process works, you are mentioning block chaining, you are mentioning block ciphers, and you're explaining how the XOR process works with the new block being XORed with the previous block. Now, one of the most common ways of encryption is symmetrical encryption, and we've been using this for centuries. You might have encountered it already. Think about the history behind the Caesar cipher, the Vigenère ciphers, and so on. In symmetric encryption, we use a secret key, and the same key is used to encrypt and decrypt the encoded message. Consider a simple system which uses 10 binary digit encryption, and this gives about 10 billion possibilities. I'm going to encode the message, computer science is exciting, and our key is going to be this number 429.1362856. And the encryption algorithm basically works this way, that each letter in a word is shifted across the alphabet, +4, +2, +9, and so on places. Once we reach the end, for example, the last digit 6, we repeat the whole process. So the next 11th digit will become 4, and then we go through the same thing again and again. Now, using my key and the algorithm, I can encrypt computer science is exciting into GQ, VQ, and so on. Do pause the video and then see if it makes sense. But if I send this message now, GQ, etc., over the internet, unless you knew the key and the encryption algorithm, it would be very difficult for you to decipher or decode this. You might try some brute force algorithm. Eventually, you might decode the key. And once you've had that, once you've decoded it, then any message that I send and you've intercepted it, you can easily decrypt it. And this leads to the key distribution problem, that how do you exchange these keys, especially over the internet? Now, modern computers could crack the key that we just looked at in about a few seconds. And to combat this, we would normally be using a 256-bit encryption, which gives 2 to the power 256 possible combination. Even this may not be enough as computers become more and more powerful. Think about this, that if your clock cycle does a few billions every second, it doesn't take you that long to cycle through a lot of different possibilities. One issue with symmetrical encryption is that both the sender and recipient need to use the same secret key. So there is that security risk that perhaps the sender has to supply the key to the recipient, and this key itself could be intercepted while that's happening. And once you got the key and you understand what the key does, all the messages can be unlocked whenever you want them to. This is referred to as a key distribution problem, and it is all to do with the interception of keys in symmetrical encryption. Now, we could probably solve it using advanced algorithms. Here is one possible solution that you can pause the video and go through. You don't need to remember this. This is just an example for you to understand that we could try some kind of mathematical way of solving things. The true solution to solving the key distribution problem is to have public and private keys. And for that, we move on to asymmetric encryption. Asymmetrical encryption uses 2 keys instead of 1. A public key, which is available to all users, and a private key known only to a specific person or perhaps is on a specific computer. Now, most banks and most financial organizations or even e-commerce websites are using asymmetrical encryption. You distribute this public key to all the customers, they will encode things, and then they will send that to the bank, and the bank will unlock it with its own private key. So on screen, you see an example of this, that Mira sends Tom her public key, and Tom will use Mira's public key to send a message to her, which Mira unlocks with her private key. Now, if Mira wants to send Tom a message, she will need to use Tom's public key, and Tom would do the same thing. The algorithms for both the public and private key are a matching pair which are mathematically linked but cannot be derived from one another. Now, you saw an example previously where we looked at how this could work, a possible solution. So perhaps you might want to rewind the video and then have a deeper look at that particular example to just get an idea on how this would work. However, there are problems with this particular approach as well. It seems safe, but there are a lot of issues. For example, how can Mira be certain that the document came from Tom and that it's not been tampered with during transmission? Because the public key is public in nature, therefore anybody could pretend to be Tom and package or encrypt their instructions or messages using the public key, and then Mira would think it's from Tom. So authentication does become an issue with asymmetrical encryption. So it needs to be paired up with other technologies like digital certificates and digital signatures to ensure we have authenticity, security, integrity, all of those. Now, one of the main problems with asymmetrical encryption is that the person in the middle could intercept the original message from Tom and repackage their own instructions using the public key and pass it on to Mira. So the organization that's receiving the message does not know whether the original message came from the person that was sending it or a hacker or somebody in the middle. This is where we started thinking about solutions to this particular problem. How could we detect interference during the transmission? So if somebody does intercept a message, can we detect that? And for this, we had to go into the realm of physics and quantum mechanics in particular. And quantum cryptography, which is the area that we're interested in, uses the properties of light. Light can traverse both horizontally or vertically, and you only know what the waveform is when you actually have a look at that particular point in time. Now, we're not going to go into deep quantum mechanics behind it, but the light could be traveling in a horizontal direction or a vertical direction. Now, you probably have encountered this phenomena if you wear sunglasses, especially polarizing sunglasses, because what happens when you put a polarizing sunglass in front of natural light? It blocks a particular type of wave. For example, if you look on the bottom left-hand corner, you'll see that phenomena. The wave is traveling, the horizontal wave is blocked by the polarizing lens because only the vertical wave is allowed, and it just travels through. And that's basically the polarizing lens acts as a filter. It blocks the horizontal wave and only allows the vertical wave in. And you could probably do the same thing vice versa. Now, it's this phenomena that is interesting for us because this allows us to then create quantum cryptography, and we'll be talking about that in a moment. However, if you wanted to try this experiment at home, you could do that. Take one sunglass or a polarizing lens and maybe have natural light passing through that. Then take another polarizing lens and then maybe adjust it at a 90 degrees angle. So you're not having something exactly the same as the previous polarizing lens, but just a bit vertical to it. Now this will allow no light to pass through because both the horizontal and the vertical waves will be blocked. Kind of like the pair of sunglasses to the left of on your screen. You will not see anything, just pitch black. However, if you put a third sunglass in the middle and just tilt it at a 45 degrees angle, you will now see some light passing through because the second sunglass or the second polarizing lens, the moment the light hits it, it resets the waveform into both horizontal and vertical again. If you want to go into the deep science behind this, please feel free to watch a video on quantum mechanics and how photons react to it. However, we're interested in this particular phenomenon. And you can try this experiment at home and chances are that you will see this working really well, or perhaps the sunglasses that you have aren't polarizing. So think about what's going on. We send the original transmission. The moment a person in the middle comes in, it changes that transmission completely. That means we can detect somebody has intercepted a message. We were expecting no light to come through, but light has come through. And that is the phenomenon that leads to quantum cryptography. So quantum cryptography utilizes the physics of photons and their physical quantum properties to produce a virtually unbreakable encryption system. This helps protect the security of data being transmitted over traditional fiber optic cables. The photons oscillate in various directions and produce a sequence of random bits, zeros and ones, across the optical network. However, before we begin sending all of this, the encryption keys need to be sent, and the encryption keys use quantum cryptography. And the protocol that is used to define this is called a quantum key distribution protocol, and the most common one is BB84, and that's no relation to BB8, just a coincidence there. Now, QKD uses quantum mechanics to facilitate the secure transmission of encryption keys. And quantum mechanics itself uses a qubit, which is a quantum bit, as the base unit of quantum data. And unlike traditional binary, which uses discrete zeros and ones, the state of a qubit can be 0 or 1, but it can also be both 0 and 1 simultaneously, just like the photon in the light wave. The light can be either horizontal or vertical, or it could be either of them, and you only know what state the light is when you put a polarizing lens over it. Otherwise, light could be either a horizontal wave or a vertical wave. You don't know. It could be 0 or 1, but it's only when you pass it through a filter at that point in time you can change it into a vertical wave or a horizontal wave. And this phenomenon is what we use for quantum cryptography. You need to understand what it is, which we just talked about, and how the process actually works. Now on screen you're going to see a series of steps. You need to remember these steps because exam questions will ask you about these steps. You perhaps might not want to understand the science behind it. You don't necessarily need to, but at the very base level you need to understand how the sender and receiver can exchange encryption keys using quantum cryptography. So let's begin by looking at this. The easiest thing to do is first have a look at the diagram so you can understand how things are working. A photon can oscillate in various different directions. So you can see the various directions a photon can go in: vertically, horizontally, diagonally. Okay? Now this photon will have to pass through a series of filters, or in this case we call them polarizers. So the effect of the 4 polarizers on a photon shows the resulting polarized photon. So when we pass it through the horizontal one, it looks like a horizontal wave. Pass it through the diagonal one, it acts like a diagonal one. And if you pass it to the vertical one, it will come out as a vertical photon. Okay, so it could be in any of those states, but once we pass through these polarizers, it acts like that type of polarized photon. So the stage 1 is that the sender uses a light source to generate photons. Then the next step is that the photons are sent through 4 random polarizers, which randomly give one of the 4 possible polarizations and bit values. So the vertical one is classified as 1 bit, horizontal one is known as a 0 bit, the right 45 degrees polarization and the left 45 degrees polarization can be 1 and 0 bits simultaneously. So this polarized photon then travels along a fiber optic cable to its destination. At the destination, there are 2 beam splitters. There is a diagonal splitter, which is known as X splitter, because it looks like 2 diagonals intersecting. And then there is the vertical and horizontal splitter, which looks like a cross, which basically is known as a Y splitter. So you've got X and Y splitters. So the photon will pass through these splitters, and then there will be 2 photon detectors at the end, which will then record their final state. So remember, what's happening is when the sender is using its polarizers, it's either gone into one of those 4 states, 1 bit, 0 bit, or 1 or 0 simultaneously. And then it comes through the fiber optic cable in that particular type of state. And then it hits this diagonal splitter or this vertical horizontal splitter. And then the photon is detected. So these 2 photon detectors are at the end of the process on the receiver's end. So these 2 beam splitters are chosen at random and the photon detectors are red. So you don't just pass them through both of them, you just pick one randomly. So the whole process is repeated until the whole of the encryption key has been transmitted from A to B. The recipient then will send back the sequence of beam splitters that were used, for example, X, 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 Y, Y, X, X, Y, Y, and so on. And it sends all of that back to the sender. The sender will now compare this sequence to the polarization sequence used at the sending station. It checks each one and says, well, okay, I passed the one through this polarizer and the receiver passed it through this splitter. Do they match? If they don't match, it's a cross. If they do match, it's a tick. And it goes through the entire list. And it identifies which splitters actually led to the correct interpretation of the original sequence of bits. And it then sends this information to the recipient and says that in this particular sequence, these beam splitters led to the correct answer. Now, this allows both the sender and recipient to be fully synchronized, because even if anyone intercepts this information on an open channel in the middle, they don't actually know what the original sender's polarizers were, and the eavesdropper would find it almost impossible to read the encryption key, making the whole process extremely secure. Therefore, encrypted messages can now be sent along the fiber optic cable, with the decryption key being used to decode all the messages. And the moment an eavesdropper tries to intercept it, the properties of the photon will immediately change, because the moment you pass it through to decode it to a beam splitter, it changes the quantum properties of the photon. So if it's going to retransmit or repackage it, it's going to lead to an incorrect sequence. So it's quite secure. It's practically unbreakable. The moment you intercept the transmission, the photon's properties change. So make sure that you remember the various different stages. Normally this will be a 4 or 6 marker, and as long as you know at least 6 of these stages, you should be able to get full marks. But of course, there are drawbacks to this particular type of cryptography as well. And currently, it requires a dedicated line and specialist hardware, which can be very expensive to implement initially. It has a very limited range. At the time of this particular video, it's about 250 kilometers, which isn't quite huge. It is possible for the polarization of the light to be altered due to natural conditions as well. And due to the inherent security system that we generate using quantum cryptography, it can be often misused by terrorists and other criminals. And they can use this technology to hide their activities from government and law enforcement as well. So of course there is a con to this as well. And again, there is the authentication element as well. Who is the person sending the data? So again, just with any kind of encryption, a number of different technologies might be needed in addition to quantum cryptography to make everything a lot more secure. Okay, we'll stop here for today. Hopefully you understood why encryption is needed and how symmetrical encryption works, what is meant by the key distribution problem, and how asymmetrical encryption works as well, especially the use of 2 keys, public and private keys. You should also be able to explain how asymmetrical encryption solves the key distribution problem. Hopefully you've understood what quantum cryptography is all about and what the drawbacks of quantum cryptography are. And hopefully you'll be able to articulate the various different stages that happen between sender and receiver to ensure that the keys are securely exchanged using quantum cryptography. That's all for today. If you do have any questions, please do get back to me. Otherwise, I'll see you in the next lesson.